This is lesson 3.7, page 156, graphing absolute value functions. One thing about this lesson, this is going to be another lesson that I would test you with no calculator, because if all you do is use your calculator, it doesn't tell me you really understand any of these things. It's just plugging it in your calculator. In this lesson, you will learn how to translate graphs of absolute value functions. We learned about translations in the last lesson. You will learn how to stretch, shrink, and reflect graphs of absolute value functions, and how to combine transformations of graphs of absolute value functions. Let's talk about an absolute value function. An absolute value function is a function that contains an absolute value expression. The parent absolute function is f of x equals x. You can see that it said here absolute value function is a function that contains an absolute value expression. You can see that here. This contains an absolute value expression. The parent function means the most basic. This is the most basic absolute value function. The graph of f of x equals absolute value x is V-shaped and symmetric about the y-axis. The vertex is the point where the graph changes direction. You can see that. I'll highlight it here, point it out in red. This point is the vertex. It's where the V comes to a point. The vertex of the parent function graph is always 0, 0. That's what they're saying here. Okay, so anytime we have the parent function, this is easy. You're going to have the vertex at 0, 0, and it's going to be a V-shaped graph. The domain of f of x equals x is all real numbers. Remember, domain is the x values. That means x can be any number, any positive, any negative number for this graph. X can be anything. However, the range, y, is always greater than 0. That's easy to see here. Let me take a highlighter and show you. Can you see how this graph is only above 0 for y? I'm highlighting that. This graph never goes into the negatives. Y is always positive on the parent function. The graphs of all other absolute value functions are transformations of the graph of the parent function f of x equals x. And the transformations presented in lesson 3.6 also apply to absolute value functions. So you're going to see some of the things we applied in the last lesson reinforced today. Now, all this stuff I read, I'm going to try to simplify it into a quick statement here. Basically, all this stuff up here is saying absolute value function graphs are always V-shaped, and that we can translate them. Remember, translate, maybe we should talk about that. We can slide them, we can stretch them, we can flip them upside down, which is what reflect means, or we can shrink them. So transformations, we can slide, stretch, reflect, or shrink them. Let's talk about graphing functions that would be related to the parent function, like g of x equals absolute value of x plus k, or g of x equals absolute value of x minus h in the absolute value. Now, these look somewhat the same, but they mean completely different things. When you are adding or subtracting something outside the absolute value, that's going to slide your graph up or down. Now, translate means slide, and that's something that we learned in the last lesson. So, adding or subtracting outside the absolute value will slide the graph up or down. If you add or subtract inside the absolute value, this will translate. It will slide the graph left or right. Now, I want you to notice the subtraction. Notice the subtraction. Your translation will be the opposite of what you think. So if you see, like here, when you see minus 2, that actually means move the graph to right, not to left. It's opposite of what you'd think. And there's one other thing I want to point out, and it'll come up again later in the video. In front of these statements, we would have a 1. In front of these, we would have a 1. This is like the slope of the graph, even though it's not called slope. Okay, so these graphs, you notice, look over here, you notice how we're going up 1 over 1, up 1 over 1, up 1 over 1, or over here, up 1 over 1, up 1 over 1, up 1 over 1. These graphs, it's not called slope, but it's like slope. They have a 1-to-1 rise to run ratio every time, okay, for the parent function. So if I want to graph each function and compare each graph to the parent function, describe the domain and range, let's do this problem. I'm going to take this, I'm going to graph the parent function, then I'm going to graph this, and then I'll compare their domain and range. The parent function is easy. Remember, the vertex is 0, 0. Can you kind of see that here? I wrote zeros in the problem. The vertex is 0, 0. And here's my slope. It's 1. That means go up 1 over 1, up 1 over 1, up 1 over 1, and do that in both directions. And there's the parent function. Let me get out my ruler and draw lines. That's my parent function right there. Okay? Now, g of x should then be easy. G of x equals absolute value x plus 3. Now this plus 3 that I'm going to circle, this is telling me to take this graph and move it up 3. Well, that's easy now. So I'm just going to get a green pen so it will match my color. So just move up 3, move up 3, move all these points up 3, and redraw the graph. Well, okay, that's easy enough. So here is the function g of x. That plus 3 is just taking this graph, the parent function, f of x, and it's just moving it up 3. This is why I'm saying we should do this stuff without a calculator. I don't need it. This is telling me take that graph and move it up 3. Okay? The next graph that they want us to, I'll do the next graph, then we'll do the domain and range of each. So now they want me to take this graph, m of x equals absolute value x minus 2, and they want me to graph that and compare it to the parent function. Now remember, be careful. Minus 2 would make you think I should move this 2 to the left, but do you remember how the equation to start had a minus in it to start? So everything is backwards from what it seems. So when I see minus 2, that actually means take my graph and move it right 2. So let's do that. Right 2, I'll move that point right 2, I'll move this point right 2, and I'll do a couple of these, right 2, right 2. Okay, time to start graphing. And here would be that graph. I moved everything right 2. Okay? Now let me get the domain and range because I forgot to do that. So for the graph in green, g of x equals absolute value of x plus 3, the domain is all reals. I can plug in any number for x. I could plug in negatives, positives, doesn't matter what I plug in. Now my range, can you see it? I'm going to use my highlighter again for this green graph. Do you notice my graph is always here or higher? Can you see how my graph is at y equals 3 or above? Can you see it from my shading? My range would be y greater than equal 3 for g of x. Now, let's move on now to this graph and write the domain and range for m of x. So I'll do that in red. Okay, my domain here is the same thing. I can plug in any number for x, so it's all reals. Okay, but now let's look at my range. I'll use a different, let me highlight this one in orange this time. Okay, do you notice how this graph is here and it just keeps on rising? The lowest my graph ever is at 0 for y, so y would be greater than or equal to 0. Let's have you try real quick. Take these two, graph each, and then compare it to the parent function, and then describe your domain and range. Okay, I'm back. So first of all, here's the parent function. I'm sketching that real quick. F of x equals absolute value x. So we have our vertex at 0, 0, and you notice up 1 over 1 to create my v. Now, let's look at h of x equals absolute value x minus 1. That minus 1 is telling me move the graph down 1. So you notice how I just shifted the graph down 1 and I did it in blue. The domain, x can be anything, it's all reals, but my range, do you notice how my graph is from negative 1 and up? I'm kind of highlighting it here. So my range would be y greater than equal negative 1. Let's talk about n of x equals absolute value of x plus 4 in the absolute values. Now, be careful here. Remember, plus 4 makes you think move 4 right, but it's actually the opposite when we are inside the absolute value. This is 4 left, so my vertex is at negative 4, 0. And you can see going up 1 over 1 each time. Now my domain and range. My domain is all reals. X can be anything. Now my range, you notice how this graph is from 0 on up for y. There's my range, y greater than equals 0. That should make this easier because now we're going to talk about stretching, shrinking, and reflecting. That number in front of the absolute value is like the slope. Even though we would never call it slope, it's like slope, which should make this easy. So when you look at this problem, can you notice we're not adding or subtracting anything inside the absolute value, and we're not doing adding or anything or subtracting anything outside. So the vertex of this problem is at 0, 0, which you can see. I'll do it in blue right here. But the slope is 2, which means go up 1, 2 over 1, up 2 over 1, then do the same thing the other way, up 2, left 1, up 2, left 1. And there is the graph, they're doing it in the book, of g of x, or q of x equals absolute value 2, I misspoke, 2 times the absolute value of x. You know the domain here, x would be all reals, and the range would be any y value greater than or equal to 0. Now when you look at this question here, the vertex of this is still at 0, 0. We're not adding or subtracting anything inside the absolute value or outside. So the vertex is 0, 0, which you see here. But you notice this is like a slope, even though we don't call it that. A slope of negative 1/2. Doesn't that mean down 1 over 2? Think about that. Okay, so let's go over here. Down 1 over 2, down 1 over 2, down 1 over 2, down 1 over 2, and you can see how we're creating that from that statement. Okay, so it should be really easy to stretch, shrink, and reflect these without a calculator. I would like you to try these two real quick. I would like you to graph the parent function and then graph each of these and then describe the domain and range. You can compare these and then describe the domain and range. Okay, I'm back. So first of all, here is the parent function. The vertex is 0, 0, slope 1, just like normal. Now, r of x equals negative 3 absolute value x. Now, the vertex is still at 0, 0, but the slope would be negative 3. So here's my vertex, and I'm going down 3 over 1, down 3 over 1, and the same thing in the other direction. So there's my v. This is reflected and stretched. You can see that. It's upside down, reflected, and it's stretched out. These points are further away from the x-axis. And the domain is all reals, and can you see my range? All my y values are below 0, so y less than equals 0. Now, v of x equals quarter x, absolute value x, 1/4 absolute value x. Vertex is still at 0, 0. Even though it's not called slope, it's like that. Slope is 1/4, which means up 1 over 4, up 1 over 4, and do the same thing in the other direction. This is a vertical shrink. Do you notice how the points are closer to the x-axis? Now my domain, x is all reals. I can pick anything for x, but my range, let me take a highlighter. Do you notice how all my values for y, they're all higher or equal to 0? That's why my range is y greater than equals 0. So what you're going to see here is what I've already talked about. It's just repeating what I've talked about. An absolute value function written in this form is in vertex form. Now they call it vertex form is because it's giving you the vertex without doing any calculating. Okay? These two numbers tell me my vertex. It tells me where my V starts at. The vertex of the graph is just whatever H and K are. Now remember, got to be careful here. Let me make a little note. This is going to be backwards from what it looks like. We got to know that. Okay? So let's graph these two. Graph f of x equals absolute value x plus 2 minus 3. And then I'm going to, instead of doing what the book has, we're going to do g of x equals 2 absolute value x plus 1 minus 3. And we're going to compare these two graphs. Okay, so for the absolute value of x plus 2 minus 3, here's my vertex. Right here, these two numbers. Now just be careful. This number is backwards from what I think. So this tells me to go left 2, up 3. So my vertex would be here at negative 2, 3. And can you see how my slope is 1? So from here, up 1 over 1, up 1 over 1, and do the same thing in the other direction. And there's my V. Okay? There's my absolute value graph for that. I'm sorry, I just realized I made a mistake here. This is an up 3. This should be down 3. It's a subtraction. So let me quickly fix that on my video. That's better. So I had left 2, down 3. So my vertex would be at negative 2, negative 3. And then there's my slope of up 1 over 1. Now, g of x, I'm left 1, down 3. So let's start sketching that. Left 1, down 3. And this one has a slope of 2, so I should be going up 2 over 1, up 2 over 1, and do the same thing in the other direction, up 2 over 1, up 2 over 1, up 2 over 1. And now I have to do is just quickly take out my ruler and graph it. Okay, and there it is. Now let's describe the translation. Here's the translation. First of all, do you notice how my vertex shifted 1 right? So we translated 1 right, 1 right, and then we stretched the graph. Do you notice how this graph, because we're multiplying by 2, we're stretching it. The points will be farther away from the x-axis as we stretch things. We're stretching it vertically. So we translate the graph 1 right, and we are stretching our graph. Okay? Stretching the graph. Let's get our domain and range. Our domain for these graphs, both of them would be all reals. We can plug in anything for x. The range, well, we can get that real quick too. Do you notice everything for y is negative 3 or higher? So my range is y greater than equal negative 3. And so to wrap up the video, we're going to combine transformations. That should be a piece of cake now. Now that you know what A, H, and K tell you, this is slope. You know, A is slope, and H and K are the vertex. It's easy to do these now without a calculator. We'll do this one real quick on paper, then we'll finish the video. So we're going to let g of x equals negative 2, absolute value x minus 1 plus 3, and we're going to compare this to the parent function. Okay, and here's the parent function, as always, vertex 0, 0, up 1 over 1 each time. And now let's get to g of x. Can you see how the vertex is 1 right, this is backward, 1 right, 3 up, so let me write that, 1 right, 3 up, let's do that, 1 right, 3 up. And then my slope is negative 2, that means from here go down 2 over 1, down 2 over 1, and then do that the other direction to create my V, down 2 over 1, down 2 over 1. And all I have to do now is get my ruler and draw it out. So there's g of x graphed. And now I want to compare the two. Let me do that. Do you notice how the vertex has been translated 1 right and 3 up? That's what I wrote here. My graph g of x has been reflected. It's opening down, and it's stretched because we multiplied by 2. It's been reflected and stretched by a magnitude of negative 2. And then my domain, let's talk about the domain and range of g of x. My domain is all reals, x can be anything, but my range would be any values for y that are less than or equal to negative 3. Let me get a highlighter out so you can see that. You can see there's the highest value, it's negative, positive 3, I meant to say. Y is less than or equal positive 3. The highest value is positive 3, and I'm just going down, okay? I think I'm going to pause the video there. If you have questions, make sure you ask in class.